Now it remains to show the asymptotic normality for A. So remember, we need to show this and this, but the latter has been cleared. We have done this, and now we are going to show this. And it is easy. You may guess. In the end, we are going to use the central limit theorem. So central limit theorem is the key result we need. So we are going to show this result, normal distribution for some variance omega. And because the criterion function can be written in this way, a sample average of something, then the first derivative, an is the first derivative, so square root n times an can be written as square root n times some sample average. And here, okay, still we need a few more steps. In the end, we would like to have this kind of form to apply the central limit theorem. The central limit theorem is about the difference between sample average and the population mean. So then where is the population mean? We can handle that easily because we know that by definition, by construction, theta 0, the true parameter, is the maximizer of the criterion function. And again, by the first order condition, the derivative at theta 0 must be 0. So, excuse me, because the criterion function is the expected value of the L function, log likelihood type function, then its derivative satisfies the first order condition at theta 0. So it is 0, so you can simply add a 0, subtract 0, so anyhow it is 0. So this part has been resurrected, we easily equipped. Then you can apply the central limit theorem. Central limit theorem is can be written this way. Central limit theorem is square root n times the difference between sample mean and population mean converges in distribution to a normal distribution with variance of this. It's my bad. The variance should be, I had to be more careful in writing the variance. Let me fix it on the go. Because I need, excuse me. What I need is okay, I will do it later. So this is right. This is what I this is what I did. And the assumption for the central limit theorem is pretty mild. Assumption is that the variance must be finite, and we define the variance as omega, and it should be finite. And remember, what I wanted to show you here is, so this variance, the variance is defined, as you know, is defined as expectation of large bracket, small bracket, and oops. So what I want you to show you here is this. So this is how we not the end of it. you may remember, this is the definition of, so variance equals to this expectation minus this, and as you know, as you can see, this part is 0. So this is 0, this is 0. Transpose does not matter. So in the end, it equals to this. So therefore, you can say that omega is this. Maybe this is a better representation. So anyhow, omega can be written in this way, L prime and L prime transpose. So the reason why I try to distinguish the differentiation and transpose is because of this. So like we have to use two notations at the same time. So I intentionally use a different notation for transpose. And then, okay, now we have done what we need to do. So what we did so far is we have shown this and we have shown this. Then we are going to combine them. Before doing that, let's think about the general property. Suppose that X is a k-dimensional random vector and M is a M by K matrix. So look at the dimension. X is k-dimensional vector and M is M by K matrix. And we define M-dimensional random vector Y as M times X. M times X is M-dimensional. So, and then if X, so now assume that X, the random vector, is normally distributed. So K-dimensional normal distribution. So omega must be K by K variance matrix. And then, like if you multiply M, the variance of Y takes this form. So you have to multiply M before and after the original variance matrix, M, but the second M must be transposed. And you need to think about, it is easy to understand if you think about the dimension. Y is M-dimensional, Y is M-dimensional, so its covariance matrix must be M by M. For this to be M by M, and the matrix M is M by K, so M by K, K by K, K by M. So you have to transpose the last one. So that's the general result. And as a special case, if the matrix is symmetric and square, k-dimensional matrix, so square K by K square matrix, and it is symmetric, which means transpose does not change anything, it's symmetric, and then you don't need to take transpose. So in this case, you can simplify like this. I am going to use the same, so if you understand this general property of a normal distribution, now you can apply that to our case. Theta is a vector, and let's assume that it is k-dimensional. So everything is k-dimensional. In the end, we need k-dimensional result, and an is also k-dimensional. Look at the definition here. Q is one-dimensional, and if you differentiate Q with k different parameters, then that derivative becomes k-dimensional. So this is k-dimensional normal distribution. So omega is k by k, and if you differentiate again, it is k by k matrix, and it is symmetric. So second derivative is, so differentiating a function with so say suppose that you differentiate a function with respect to twice with respect to x and y equals to the differentiate twice differentiation with respect to y and x. So the order of differentiation does not matter, so it is symmetric. Think about, again, if you don't understand this, open your calculus book and see how the second derivative is defined, that it should be simple to understand. It is symmetric, and then obviously its inverse is also symmetric. So the limit is symmetric. So everything is symmetric. Therefore, you may simply write it this way. in general, we had to write, so there is a minus. Remember, we had a minus here. And it does not matter in the end because you have, so minus Bn inverse converges to minus H inverse. So you have to multiply minus H inverse before and the after guy must be transposed, but the minus canceled out, so multiplying minus twice disappears. Then transpose does not matter, so as a result, finally you have this formula. So usually we call this a sandwich variance formula, because variance is multiplied before and after by the same guy. So it's like sandwich. So we have learned a lot of theories, a lot of assumptions. So I summarized everything in one page. I am very proud of this. It took a lot of time for me to make this diagram. So these are the underlying assumptions we so far considered. So theta hat uniquely maximizes the criterion function, and the parameter space is compact, and the criterion function is continuous almost surely. Then from here up, it should be almost surely. Then from 1 to 3, you have ID conditions for ID condition, which was used for consistency, and then so the ID, and for uniform convergence, 2, 3, 4 is required. 2, 3, 4 are required. So then 2, 3, 4 imply uniform convergence of the criterion function. Then combining ID condition and uniform convergence, we had consistency. Consistency was proved based on these two conditions, which are implied by these higher level conditions. And then number 2, number 5, number 6 imply another uniform convergence. Uniform convergence of the second derivative. Second derivative uniformly converge, and it imply, and Taylor expansion requires continuity, and then Taylor expansion implies the intermediate value converge, and together with consistency implies consistency of the intermediate value. And combined with uniform convergence, we have Bn converging to H, and with non-singularity of H by continuous mapping theorem, we have Bn inverse converging to H inverse. And also to have this asymptotic normality, we have first of the condition from the maximization condition, and so it implies mean 0, and the finite variance condition also like together with mean 0 and finite variance, implying the central limit theorem here. So combining the central limit theorem and this convergence, and the convergence to a constant matrix, and the expression we obtained from Taylor expansion, combined together to the final result. So so 1, 2, 3, 4, 5, 6, 7, 8. There are 8 conditions, but actually this condition, the continuity of the second derivative, automatically implying continuity of the original function. So for the second derivative to exist, the original function must be continuous. So this condition is implied by this. So you don't need to worry about this. So in the end, 1, 2, 3, 4, 5, 6, 7. There are 7 assumptions, and from this relationship, you get the asymptotic normality assumption result. And as I said, the reason why I'm telling you this is because asymptotic normal distribution is it's common. It's not uncommon, it's very common. But at the same time, in practice, what you need is the variance formula. So the variance, you may need to calculate the variance of an application. So to handle those applications, you need to understand how it works. Okay, thank you for watching. I hope this helps. Yeah, try your best. See you later. Bye.